Hey, good afternoon, everyone. Good afternoon. How's everybody?
Good afternoon, Professor. I'm
Ah,
okay, and
good.
yourself?
I'm good too. I'm good too. Nice to hear from you, Malaysia. Let me take care of a couple of things first. Okay, so make myself a moderator. Okay, and okay, so we have currently four people. Good afternoon, Rostam. Afternoon. Good afternoon, Coral. Alejandra, are you there? Alejandra? Oh, yeah, yeah. Good afternoon, Alejandra. Good afternoon. All right, so we are we're now moving on to uh, since yesterday, right? We uh, we're into topic three, which is time value of money. So we already went through single cash flow model, future value part one, future value part two. And yesterday I noticed this should be present value part one, present value part two, but it was mislabeled as FV part three and four. So I just, made a correction there. So, we're now moving on to present value uh, part one. Okay. So, but before we play this video, do you have any questions so far about the time value of money? I mean, we've done only a single cash flow future value only. But any questions so far about the future value, single cash flow future value? Well, it's basically, compounding, right? The main idea is compounding, right? And if you understand compounding, I guess, and the only thing that was added, only new concept that was introduced was the concept of M, right? In other words, how many times the compounding takes place in a year. So it's a compounding frequency. It can be annual or monthly or semi-annual or quarterly or daily even, right? So now, if you don't have any more questions, right? Let's start on the video number three. Okay?
Uh, let's think about a couple of other questions, right? We already know, since we all know that basically compounding. Oops, I'm sorry. I'll have to choose. I'll have to select. Yes, okay. So we know the compounding, right, is uh, the very basic compounding formula is FV equals P times 1 plus R raised to N. And we've used that example of, let's say, making a deposit of 10K and just to make it simple, keeping it there for 2 years. Okay, when interest rate is 10%, right? And we already know the answer. I mean, it's 12.1K, 12.1K. Let me write it. 12.1K, right? Then we can flip the question. We can flip the question and see, ask a question this way. So if I am entitled to a 12.1K 2 years from now, or if I want to receive 12.1K from 2 years from now, if the prevailing market interest rate is 10%, how much do I need to put into the bank today? Right? In other words, what should be my principal today? And we already know the answer. I mean, if interest rate is 2%, right, and you want 12.1K 2 years from now, then the answer is you have to put 10K in the bank now, right? But also, the principal should be 10. Also, the question can be rephrased this way. So then, if I'm going to receive 12.1K 2 years from now, I have some, let's say something, I have an entitlement or claim to this 12.1K. And what gives you that entitlement? Something like bond, right? You have a bond that matures in 2 years, and when it matures, it pays you 12.1K. It could be a bond or some kind of certificate, like CD, that entitles you to a claim to 12.1K 2 years from now. And so you have this bond or CD or some kind of commercial paper or investment instrument, right? That will mature in 2 years, giving you 12.1K. Now, you have but you are running into a cash flow problem right now. Currently, you are undergoing a cash flow problem. You're very tight with cash, right? So you have, but then it's not like you have nothing. You have 12.1K, but this is not today's 12.1K. It's gonna, you will have 12.1K 2 years from now, and you have a certificate that entitles you to that 2 years from now. So this is this CD or bond is worth something, right? It's worth 12.1K 2 years from now, but you don't know. Question is, you don't know how much it is worth today, because it will be 12.1K 2 years from now, but not just yet. But then, since it is at least worth something, if you sell it today, and if you cash it out today, then how much is it worth today? That would be another question, right? How much is it worth today, right? In other words, how much can you sell it for, and how much will the buyer? How much will the buyer pay? How much will is the buyer willing to pay? And the answer is, it is worth 10K today. Exactly. Why? Think about it. If a buyer is willing to pay something, and because if he buys it, he can hold it for 2 years until maturity, and he will get 12.1K. Then what's he gonna pay? Well, he will be paying exactly 10K, no more than 10K. No more than he is willing to pay no more than 10K, and you're willing to accept no less than 10K. Why? Think about it. If he has a 10K today, he can put it in a bank or in a CD, because the prevailing market interest rate is 10%. 2 years from now, he will get exactly 12.1K. So why is he offering anything more than 10K? There's no reason for him to offer anything more than 10K. And just for the same reason, you are not willing to accept anything less than 10K, right? So this 10K is, of course, the principal of 12.1K today, if the interest rate is 10%. So mathematically, this is a question about solving for principal. And how do you solve for principal? Look, I've been telling you over and over, all equations are basically a question of whether you can identify or not the z equals x times y structure, right? And if you can identify the structure, what is x? How do you solve for x? X is then z divided by y, right? And also y equals z divided by x. Isn't that right? So it's really, all equations are basically a question of whether you are capable of identifying this structure. Once you identify the structure, then it's easy to solve. And no matter how complicated this one is very easy. It's very simple. This is z, this is x, this is y. So all you need to do is simply, so you're solving for p, then it is simply future value over 1 plus r raised to n. Okay? And this is called present value. Okay? In other words, principal is present value if you're looking at it from the future, right? If you're standing in the future and you look at the present, I mean, if you're looking at the present from future, the present is past, but from futures.
Most people have no clue that in 2023, the best way to make money on Amazon is not with physical.
This is
point of view.
This is what happens when I post, these videos on YouTube. Never mind. I just try to skip it when that happens.
Principle is called present value. Makes sense? And see, no matter how complex, I mean, this is fairly easy and straightforward, right? And no matter how complicated, right? No matter how complicated, if you can identify the structure, right, you can solve any equation, right? Now, let me, that was too unnecessarily, the equal sign was too large. Okay, now, so in our example, all you need to do is, to find present value, all you need to do is divide 12.1k by 1.1 raised to square. I mean, I don't need parentheses here, okay? Because it's obviously a number. And then you can use your calculator and Excel, your computer comes with a calculator, and I don't know if you can see this calculator. Let me try to stop sharing and let's see. Go back here and share application screen from. We can do this on Excel, but I'm just trying to show you. You'll have to from your computer, right? From Start menu, you can pull up the and you'll. Normally it is set to standard by default, but you want to select scientific, right? Because now then do this 12,100, right? 12.1k. We divide it by 1.1. This is x raised to y, so on some calculators it may be that caret, the cone sign, right? You raise it to 2. Hit enter, you will get exactly 10,000. Okay, did you get it? Alrighty, so let me go back to okay, that's what you see now. And we know what it's going to give you. It's 10 exactly. Now, so if you think about it, this is a reverse process of compounding, isn't that right? It's a reverse process of compounding. We started from compounding is basically we started from compounding formula, and compounding is basically a process to find the future value. And the reverse process is the process to find the present value, and this process is called discounting. Okay, the process to find the present value, right? And the reverse process of compounding is called discounting. Now, also our next question is, suppose you have 10k today. We all know, I mean, this is the example we've been using. So without further, explanation, the assumption is that we have 10k today, and in 2 years, you want to have 12.1k for future value, right? Then think about it. What's missing? What is missing? What's missing? Isn't it the interest rate that's missing, right? In other words, if you want to have 12.1k, and when you have 10K as principal, right? The question is, what should be the interest rate? What is missing here? What's missing is, again, interest rate, right? What's missing? So how do you find interest rate? So basically, we start from looking at the compounding formula, right? Looking at the compounding formula, right? It's the question about R, which is, the unknown in this case, right? And then, so solving for X, unknown X, but the X is R here. So how do you solve for R? Now here we need a little more. We need a little more technique and a little more math knowledge, but whatever we can do, we should do whatever we can do. And what we can do is we need to turn it into a more simplified form. I mean, this is the simplest form, but what I'm saying is, since R is the unknown that we want to solve for, right? So let me do something. Let me do this. We need to solve for R, we will need to isolate R. But is there any way we can isolate R directly from what it is now? No, there's no way you can isolate R. So we'll need to only, because R is part of this term in the parentheses, and raised to power, raised to nth power. You can isolate, the best you can isolate for now is just this term, right? You remember, this is like, solving, this is like solving this equation for y, because this is our y, then 1 plus r raised to n is
Hey, it's Tony Robbins. I got a question for you. Who wishes they invested in Tesla before electric?
FV over P. Okay, so you're okay up to this point, but then our next question is, to isolate R, first we have to get rid of this exponent, right? It's almost like once this exponent is gone, then it's simple. If this is gone, then all you need to do is subtract 1 from both sides, and you can isolate only R. But the problem is, how do we open up this? It's like a exponent. It's like a padlock, and once you open the padlock, then it will be easy. Well, how do we do that? Huh? Okay, so to solve this problem, we need some understanding of basic algebra. Now, let's first think about the very basic example of exponent, right? So x squared, right? And x cubed. Now, first of all, we know if we take the square root of x squared, right, it will turn into x. We can lose, right? We can get rid of this, exponent. Now, another way to write x squared is actually, square root of x squared, x of x squared raised to half power. Okay, half power is another way of denoting or meaning square root. Now, and if you remember from basic algebra, right? Some rules of algebra, right? X to the raised to a times x raised to b is x raised to a plus b, and x raised to a raised to b is x to a times b. Okay, now let's check. Probably when you took algebra, you probably simply memorized it, or just without too much critical thinking. Critical thinking always requires steps of verification, but without verification, you just memorize it by rote, and that's why it doesn't stick to you. That's why it doesn't last long time. You forget right after the semester is over. Now, let's try an example. Suppose you have 2 squared times 2 cubed, right? 2 to the 3rd power. What is that? It's 2 to the 5th power by this rule, but let's check. So 2 to the, we all know this is 4, right? So it's 4 times, and then this is 8, right? 4 times 8, 32, which is exactly 2 to the 5th, right? Right, raised to 2 plus 3, right? Now then, this rule can be also easily verified. There are a couple of other rules, but we don't have time for that. We're going to revisit it later. Try the same thing. If you have 2 squared, this is what's wrong with. You have 2 squared, raise it to 3rd power. What's it going to be? It's 4 to the 3rd power, which is 4 times 4 times 4, right? It's 64, right? 14 times 4 squared, right? 16 times 4, right? 64, which is what? Which is exactly 2 to the 6th power, right? You can verify easily, right? So this rule works. So, but think about it. By this rule, this becomes what? X raised to 2 times 1 over 2. 2 times 1 over 2 is 2 over 2, which is just 1. Which is x raised to 1, right? Which is x, right? So try that again with x to the 3rd power. Now, that means to turn it into x, we'll need to take the 3rd root or 3rd radical of x. The 3rd radical or 3rd root or cubic root is written this way. Actually, square root is also original. It should be written this way. That means it's square root, right? This is the cubic root. Another way of writing it is x cubed raised to 1/3, right? If raising to half power is square root, raising to 3rd power is the 3rd root or cubic root. This is not very important, but I don't like it. And then by the same process, right, becomes x itself, just right. So now let's generalize this. We know how that means. If you raised, if you have, I'm sorry, why is it so? X raised to n. If you want to turn it into x, you'll have to raise it to nth radical, 1 over, which is in other words nth radical, 1 over n. And through the same process, right? X raised to n times 1 over n, which will be exactly then x. Now, this is the properties of exponent that we need to solve for that problem. So we'll talk about more about it in the next video. This is the end of the video, so I'll stop recording.
All right, so that was present value part 1, and we just review the process of some rules of exponents, right? And so we're going to move on to part 2. Right? Move on to part 2. But before we move on to part 2, any questions so far? Any questions? Any questions? All right, I'll take it as no, and let's.
To go on with the our question about the solving for R, the solving for interest rate. Well, we had to go through basic, properties of exponents in the previous video. Just a couple of more things, just to be, just to clarify and to just to shed some light on, what you just memorized by rote. For everyone would understand, everyone would basically know that anything raised to 0 is what? 1. Some people might say 0. That's anything multiplied by 0 is 0. But this is why it is fundamentally problematic. When people just when they make you just without logical and deductive reasoning, now and critical thinking. Now, the reason that anything raised to 0 is 1, I'll explain that. Using one of the properties that we used. So there's something that bothers me. So let me clean that out. Okay. Now, why? First of all, using these properties, right? One of the properties was this: x to the a, x raised to a, times x to raised to the b is xa plus b, right? That's me right? So let's try that. So suppose, you have f squared, I'm sorry. F squared then times x to the negative 2. Okay. By the way, you all know what x to negative 1 is. What is x to negative 1? Raised to negative 1. It's the reciprocal, right? It's 1 over x. Okay, that means x to the negative 2 is 1 over x squared. So then we can rewrite this. But by the rule, right? By the exponents rule, this will be x squared plus, right? Minus 2, right? Which is then, of course, everyone would know is x to the 0, right? But then why is it 1? Now, to answer that, right, let me write it back here. So we all know x squared times x to the negative 2, and x to the negative that's x squared times 1 over x squared, right? Using this rule. And what is this? They cancel out, right? This is 1 because it cancels out. Makes sense? They cancel out, so it's 1. Therefore, x raised to 0 is 1. Anything raised to 0 is 1 by the same, Okay, all right. So enough of that. So now let's bring ourselves back to this question. So we were stuck there. We were able to isolate all the way up to 1 plus r raised to n is fv over pv, or p, right? Now you understand p is also called, principal is also present value, right? Now remember, to lose this exponent, right? It's x raised to n. Then to make this, to make it 1, what do you need to do? You will need to raise it to 1 over n, right? Makes sense? Taking the nth radical, which means, I will have to write this over n. we are going to raise it to 1 over n. Okay, over n. And then think about it. If you raise, this is an equation, that means the left-hand side is equal to the right-hand side. So to keep that equality between the two sides, then whatever you do to one side, you must also do the same to the other side. So I raised the left-hand side to 1 over n. So what does that mean? You'll have to raise the right-hand side also to 1 over n. Right? Makes sense? Then what's going to happen to the left-hand side? N and 1 over n will cancel out. So, I mean, this is not a difficult thing, but, so I'm going to simply, whatever is in the parenthesis, right? I'm not going to rewrite it, but, but this means, the thing in the bracket, right? The thing in the parenthesis. And we know it cancels out, so it's going to become 1. And this will become 1. And the right-hand side, the thing in the parenthesis will still be, there. Now, I'm going to bring it over here, right? So if I bring it over here. So in the parenthesis, in the left-hand side, now, only 1 plus r remains. And in the right-hand side, only the thing in the bracket remains. And the thing in the bracket is fv over p, right? Or present value raised to 1 over n. Now, solving for r means, just isolating r in the left-hand side. What do you need to do? You'll subtract 1 from both sides, right? Or, transpose, move 1 to the other side. And what does it become? fv over pv, or p, right? Raised to 1 over n minus 1, right? But now, doesn't that look a little familiar? You saw this somewhere before, right? I hope you haven't forgotten. I mean, it wasn't that long ago, right? You saw this in the when? In the first topic, ROI. And what was it? In ROI, there was a name for this. What was that? It was called the geometric average. Wasn't it right? What was the formula for geometric average? At the time, we used, G, growth rate. And I told you the growth rate is, it's basically a return, right? Rate of return, average rate of return. But when there is only capital gains, right? No incidental income. In other words, only in scenario 1, growth rate is exactly the rate of return. But in scenario 2, growth rate and return are different, because in scenario 2, there is not only capital gains, but also additional income, right? Incidental income. And remember, in that geometric average, the future value was expressed as P sub t plus n, and the present value was pt, right? P sub t, P subscript t, and over 1 over n and minus 1. Remember that? Hence the geometric average, which is, and this is how the geometric average formula was derived. Because I've been telling you from in the first topic that there's a compounding going on, and when there is compounding, the average cannot, the growth rate, the holding period return can be annualized, but it has to be the geometric average. Why? Because of this, because it's compounding. And in compounding, we solve that basic compounding equation of future value equation for R. And then we come to this. And at the time, I couldn't show you how it is derived because you are not ready for that. But now you see how it is derived, okay? So once you know these connections between different variables, right? You don't have to memorize anything. Some people ask me, Professor, do I need to memorize all the formulas? I mean, there are lots of formulas, and some people feel daunted and overwhelmed. It's too much. But look, smart people do it in a smart way. They don't just, do it by rote, right? If you understand how it is derived, how it came about, right? And if you can replicate the process, then you don't have to memorize anything. Now, our next question, then our next question is, so our next question is then, I hate to, since there are 4 variables, right? First, okay, let me use this. Let's do this quickly. We know there are 4 variables, right? Why? First, future value, that's one variable. Then present value, that's another one. R, that's another one. N is the 4th one, right? When future value is the unknown, we find the future value this way. And when P is the unknown, we find the present value this way. When R is the unknown, we find R this way. Our next question is then, how do we, what if we don't know N? Well, we will solve for N later, but then let's go to an example, right? So let me stop sharing this and go to, so our next question is, next example is, okay. Let's find R or APR, right? And then let's find also present value P, right? So in this example, this is the example we already know. Future value is this, 13,000, and APR is this, right? Time is this, right? Compounding frequency is quarterly, right? This one, annual, right? Then what is the present value? Present value is future value, right? Simply future value. Discounting, right? 1 plus APR. It has to be R, but R is what? APR divided by M. You have to adjust that annual rate by compounding frequency, right? And then raised to 5 times M, right? All right. Then what do you think? What do you think we're going to get? We're going to get exactly 10,000, right? This one is not exactly 10,000. Why? Because, let's see, because this is probably pointing to the wrong, what is this pointing to? E2. Oh, and in E2, E2 is actually, annual compounding. So let's find the, this should have been E4, right? If it is this should have been, in other words, E2, right? If the future value was, this, 13,468, and compounding was quarterly, then it will be exactly like this. And we'll, this is annual compounding, so let's see what's in there. It's pointing to E3, which is not the case of annual compounding. It should be this. Okay, and if I find, you don't have to solve it again. You just simply, drag it down. Then it's not the number that was copied; it's the formula that was copied. And because anyway, D13, which is one doesn't affect anything. It's innocuous, but it's better to keep the formula uniform and consistent. Okay. Now, so that was the example of discounting. Let's go to a example of finding R rate, right? So here, looks like you have $10,000 today, and
okay, these examples, of course, I showed you where you can find them. This is Excel. Oops, yeah. This is that Excel file, right? This is that Excel file. And another thing, I mean, when I'm demonstrating it in the video, right? If possible, I want you to do it on your computer as well. But the problem is, you have only one computer. If you have only one computer, you have to use that time to watch this video, and you cannot pull up Excel file, and you cannot do this at the same time, because one screen can do only one thing, right? So if you have only one computer, that's impossible. But if you have two computers, you can watch this video on one computer, and on the other one you can download that file, or if you have already downloaded it, you can just open that file and you can work on the next screen, right? Next monitor. I mean, even if you don't have two computers, these days, you can have a second screen, right? I mean, you can buy I don't know if you, um, of course, it costs, money to buy extra monitor. I have 27-inch monitor that I hook up to my laptop, and so sometimes I use both screens. So that would be ideal. Again, uh, you cannot do this. You cannot emulate my work while watching it. So think about a way of getting an extra screen or um, extra monitor. Uh, well, of course, if you can afford it, but if you can't, just watch this very carefully, and then after class you can practice, right? All right, let's continue.
You want it to be in 5 years, you want to grow it to $30,000. Okay. In this case, it's just a given number. This is not the given number. You see, the formula is filled in. So once we have the correct rate there, this is going to look different. But let's do this first, because when this is the unknown, all the other variables must be known, right? Because we are solving for the unknown, right? To solve for the unknown, other inputs must be given. So here, according to our formula, right, is future value over present value, right, and then raised to 1 over n. But here, what is n? N is t times m. N is not given, but if we, even though m is not given, we build it, right? We build m into n, so that the n would be t times m. Then it can handle any situation. It can handle whatever the m may be. Now t is in C16, and I would like to click in C16, but you can't. When the formula is the cell containing formula, and the formula is showing, it's hovering over. I mean, it's covering C16, so you cannot click it in. In that case, you will just need to type it in, right? And then C16 times then D16. Okay, and minus 1. All right, now because D16, this column, D column is not filled in, it contains no data. Excel will automatically recognize it as 0. It may, and then it will show you. I mean, the way it is now, it might show you that it might display error message. But let's see why, because this is blank. So in this case, I'm gonna let me try entering 4 there, right? There you go, I got that. Okay, so now what if it is 1? Annual compounding. I would have to take this high interest rate to get to to triple your money, right, in 5 years. Now let's keep it at 4, and in this case, this is what we want to solve for, right? I used some function called growth, but don't worry about it. We'll try a different. So let's make this equal to that. Meaning our m is Okay. Now look at the scenario. What does this mean? You have $10,000 principal, and in 5 years you want to grow it to 13,468. Okay. What should be the interest rate? What kind of interest rate will grow it to this in 5 years? Right. So this is actually not APR. This what we found here is actually periodic rate, right? Because so let's see if it is periodic rate. So if we can turn it into APR later on, right? So in here, we will copy this because that's the and if it gives us 1.5, it's the correct one. Now I'm gonna copy that and paste here, and I'm expecting 1.5% there. Voila, isn't it? So in other words, currently this is periodic rate, not APR, right? Currently, what is in here is the periodic rate. So when you build the model to solve the problem, you cannot just mindlessly, copy the labels from the previous problem. You'll have to make sure that what the label says really means what it means what it has, what it really, So in other words, it must say what it means. So here, if you left it as APR, then you're wrong, because clearly this is not the annual interest rate that would take you there. Annual interest rate was what? It was 6%, right? And also remember because compounding frequency is 4, right? If I made it 1, you remember, if I set the compounding frequency to annual, then it was this, right? And then so actually to turn it back to the annual rate, because all the rates must be expressed as annual, what do you need to do? All you need to do is just make an adjustment, right? In other words, if what I got there is a quarterly rate, simply by multiplying it by the compounding frequency, then you will turn it into annual rate. Okay, the annual rate here. In other words, what do you see here? From here to here, that was what gave you the periodic rate. Then if you multiply it by 4, because quarterly it is something, then if you multiply it by 4, that will give you an annual rate, right? And I do the same thing here. Copy that, paste it here. It's going to give you exactly 6%, right? Now, previously when I had just 1 there, then it was and it was showing 24% something, but that was not the same thing, because it's not like converting quarterly rate back to annual rate. It's like starting from the annual rate from the scratch, starting with the annual rate from the scratch. So it's a different thing. Now, but this checks out. I mean, we can confirm that we got it right by checking it with the original scenario. The original scenario is like this, right? In the original scenario, everything was known except for future value, right? But here, everything else is known, future value is known, and everything else is known, but APR. But then, if you solve for it first for periodic rate, and then making an adjustment to convert it back to annual rate, which is a very easy process, because anybody can understand. If quarterly rate is something X, to convert it into annual rate, just simply multiply it by 4, right? Which is what was done here. But none of this is hard-coded, right? One thing you have to remember is you don't hard-code anything. Remember what hard-coding is? Actually entering numerical data into the formula. You don't enter numerical data into formula, right? Okay. All right. So that's it for this segment of the video, and I will see you in the next video.
All right. So any questions so far? Any questions? I guess at this point, without doing the actual exercise, right? You wouldn't have actually. You need to run into actually this. You need to run this on your own, and then you might run into some problems, and then you have questions. So at this point, I don't think you have questions, but feel free to ask. If you have any questions, just feel free to ask anytime. Okay? All righty. So next, So next video is, our fourth variable is n. So let's think about, how we do that.
Pre-recorded lecture for time value of money, and today's topic is, as we discussed, a single cash flow model. So in our last class, we discussed how to solve for the rate from the base compounding model for future value, right? So there can be, in this base model, there can be 4 possible questions that can arise from this model. First, the obvious one is when the future value is the unknown, and we know then it's principal times 1 plus r raised to n. Now, the second possible question is when the principal is the unknown. If the principal is the unknown, we need to solve this equation for principal. That means future value is known, rate is known, n, the time periods, number of periods, or number of compounding periods are known, and the principal is the unknown. When the principal is the unknown, that is also called the present value, because if you solve for that principal, then how do we solve for that? We discussed it. All equations, no matter how complicated it may look, or they may look, they can be solved if you identify that z equals x times y structure. And this base formula already lends itself to that structure. As you can see, you can consider this as x. This is, z, and principal as x, and this chunk as y. And then, since x is our unknown, and you would solve for that by z divided by y, by dividing z by y, also, principal can be solved by dividing fv, future value, by 1 plus r raised to n. Now, so another scenario, another possible question that can arise from that is, of course, what should be the rate? Of course, we discussed it in the last class, so we're not going to talk about it in detail. But basically, it's a conceivable question. You have $10,000 today, and you're in 3 years you want to grow it into $50,000. So then the relevant question is, what should be the rate, right? And just like that, n can be the unknown. In other words, another conceivable question is, you have $10,000 today, and the prevailing market interest rate is 10%, and you want to grow it to $50,000. Then the relevant question would be, how many years will it take, right? So that is a fourth question that can arise from this base formula, or this compounding equation, right? So basically, I'm showing you the formula and the steps of derivation here, but as I said, to identify that z equals x times y structure, you will have to simplify the formula to the best that you can. So our unknown is n. Now this is a problem. We can't isolate n immediately directly because n is an exponent. And how do you solve for an exponent? So anyway, we will need to isolate this term, 1 plus r raised to n, because we cannot get to n directly. We'll have to get to whatever you can. So first, I would isolate this term. So then, in the left-hand side will be FV over PV. In the right-hand side, I have isolated 1 plus r raised to n. And then suddenly you notice that it makes a jump. You see ln of FV over PV in the left-hand side, and on the right-hand side, you see ln of 1 plus r raised to n. Now suddenly, what is ln? ln stands for natural log. Now the question is, what is natural log then? Well, you understand what logarithm is, and if you are not familiar with it, let's get to the basics, right, of logarithm. So I will need to change switch from this PowerPoint to whiteboard. So let me give me some time to transition, right? Stop sharing this PowerPoint, and I'm going to go into basically, you know, what. Oh, I'll have to use this pencil, okay? Okay, this 10 squared. This is not easy to. And 1,000 is 10 to the third power. And if we keep going, we can do it like this. I mean, even if it is, you know, 1 million. Comma was right, actually. I should have put comma there too. 10 to the sixth. And then what is 1 billion? 1 billion is 10 to the ninth, because 1 billion is 1,000 million, right? Now, these large numbers are very cumbersome, because putting zeros, zeros already, so many zeros, that's already very exhausting and annoying, right? But there's a better way of representing them by the exponent, right? So powers of 10, 10 squared, 10 cubed, 10 to the sixth power, 10 to the ninth power, and all these things called the power function, right? Or the powers of 10 in this case would nicely make the numbers compact, right? Now, there's another way of expressing it. We can use log, which means, you know, log of 100 to base 10. We know that means we're taking, we want to express this 100 by only the exponent of 10, right? So that means, you know, again, I can write it as log of 10 squared to base 10. Okay, and then this can be written as 2, meaning when you take the log of 10 squared to the base 10, you can express that number, you can express that only by the exponent. But how is this possible? Well, because when you write in log, I mean, if I can rewrite it as, okay, this, I will extend this equal sign here. If you rewrite it, it's like 2 times log of 10 to base 10. In other words, the exponent can be brought down like a multiplicative term. Why? This is possible because what is log of 10 to base 10? What do you think it is? Log of 10 to base 10 is simply 1. Isn't it right? That will be simply 1, right? This number. Because it's 10 to itself, right? It's 10 raised to 1, and then, 10 raised to 1 is itself, right? Log of 10 to base 10 means simply 10 to 1. So because log is basically a way of expressing a number as an exponent to the base. So this term becomes 1, I'm sorry. And then times 2. So that becomes 2, right? And likewise, 1,000 can be expressed as log of 10 cubed to base 10, and by the same procedure, it simply turns into 3. And then what about this? 1 million will be 6, and 1 billion will be 9. In other words, all these exponents can be used to compactly to express these large quantity in a more manageable and compact way, right? Now, and it's this properties that of log. In other words, when you have log of x raised to y, of course we assume that the base is x, right? Base has to be x, and you can write it as y times log of x, right? And what does this mean? This is a multiplicative, right? This is a multiplicative structure. In other words, we turned power function structure into a multiplicative structure. Now you remember what this means, what is, how this can help us. If you guys are okay, I'm going to erase all this. Okay, so remember, we had a structure z equals x raised to y. That was the structure we had, remember? Well, I cannot go back to, at this point, to PowerPoint. I will have to switch the screen, and it's going to, disrupt everything. So just remember that to solve for n, we had to do, remember, FB, we had to isolate n, but since there is no way you can isolate directly n, you had to isolate whatever you could. And it was like this, right? So think about it. What is this? This is exactly z equals x raised to y structure, right? You see the parallel in structure here. This is z, this is x, this is raised y. But then think about it. All equations can be solved if you identify that x times y structure, right? That was why we were trying to reduce this to the simplest form. But then we got stuck because it was like this. The structure was this, not this. But then we also learned that if you saw that if you take log of x, right, raised to y, then it can be rewritten as y times log of x, right? So we found that we can convert this power function structure into x times y structure, right? So then our question is, okay, so that means, oh, we can transform this into log of z equals log of x raised to y. Now, you'll have to take the log on the left-hand side as well, because if you take the log on the right-hand side, whatever you do to the right-hand side or one side of the equation, you must do the same to the other side of the equation. Otherwise, this equality won't hold. Okay, so then this can be rewritten as, we all know, y times log of x. Now, what does it look like? The left-hand side is still this. This is the left-hand side, right? And this is the right-hand side. And the right-hand side is now, the left and the right-hand side is now z equals y times x times y structure, right? Log z equals to y times log of x. So then what do? Because y is our unknown, and that's what you want to solve for, then you can simply divide the left-hand side, log of z, by the right-hand side, which is log of x, right? The problem solved. So this way, in other words, this is n, right? And if you take the log of the left-hand side, take the log of the right-hand side, right? You'll be able to find n. Now, then our next question is then, can we use, then, let's get back to common log. So let me erase this. Let me get back to common log. The log we understand, the log we know up to this point is the log using 10 as the base, right? Right, like, log of 10 to nth power to base 10. And this is called common log, right? There are largely three types of logs: common log and binary log. Binary log is log using 2 as the base. So in binary log, and think about it, 4 is 2 squared, so it's going to be 2. And 8 is 2 to the third power, so log of 8 to base 2 will be 3, and so on. And then natural log. Natural log is a log using e, or Euler's number, as the base. That e is called Euler's number. Now, some people pronounce it as Euler, but that's not right, because Euler was a German mathematician in the around 17th century, and two of the big names in math, two of the big names that gave birth to modern math are Euler and Gauss. There are other, great names like Laplace, Lagrange, who are French, but Euler and Gauss are German mathematicians, or Swiss German. And in honor of his heritage, it's not pronounced Euler, it's pronounced Euler. So it's not anglicized. Not everything needs to be anglicized. But anyway, our next question is then, what is Euler's number, and how does that allow, or how does that enable natural law? Okay, so to answer that question, we will have to switch back to the PowerPoint. So let me switch back, and then okay. And let me go back to okay, so there it is. And the volume might be you might need to the volume on the video may not be quite audible. I mean, you may not hear the volume on the video. I will provide I have already provided link to this video in the temporary folder. So if you don't hear the audio on this video, right, please visit the temporary folder and you will find the link. Okay, all right, here we go.
The two most common logarithms used are log to the base 10 and log to the base 10.
Okay, this video is embedded, and I thought this would. It has no sound. I thought, but let's see. It seems to have a sound, so let's take a listen. Oh, okay, this is not good. So that's why I posted a separate video here. Let's take a listen.
Are your kids in grades 6 to 11? Harvard has made SAT and ACT score submission optional in its admission.
What is E? The two most common logarithms used are log to the base 10 and log to the base E. Why are they the most commonly used logarithms? How do we really understand them? Log to the base 10 is kind of intuitive. It's easy to talk in multiples of 10. 10, 100, and so on. Log to the base 10 gives us an easier scale to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. 1000 to the base 10 is 3. And we can see that the multiples of 10 can be managed with a scale of natural numbers. But log to the base E is what I'm deeply interested in. It's called the natural log. And it's also written as ln. Yes, log to the base E is also written as ln. So log 20 to the base E can be written as ln of 20, the natural log of 20. What is this E? Some call it a magical number. Some call it an irrational constant. Some call it a Euler's number. But the harsh truth is this: very few people actually understand what E is. To get to E, we first need to understand growth. Let's say a particular thing doubles every time period. On this timeline, this is today, and every unit is one time period. Assume you have $1 with you. At the end of the first time period, this dollar doubles and you have $2. At the end of the second period, $2 double to become $4. And at the end of the third period, we have $8. How do we look at this growth? First, we see that the numbers at the end of the time periods are powers of 2. It's in the form 2 to the power x, where x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100% growth every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grew to $4. 2 plus 100% of 2 gives us 4, and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you're getting a 100% return on your investment. But hold on, we are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growth in steps here. What about the time in between two time periods? We are seeing no growth in between. No growth and it suddenly doubles. Again, no growth and suddenly doubles. But hey, that's not how nature functions. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows. When we started, we used to get around 30 views a day. And after a year, we started getting around 4,000 views a day. It doesn't mean our view count just jumped one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of $1 growing over 1 year at a 100% growth rate. First, we look at the annual growth. Based on what we saw, at time 0, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last day. To make it slightly better, let's divide the year into 2 equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% in the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happens in the second half? $1.50 remains as is. The growth is 50%. So 50% of $1 will be 50 cents. And this time the 50 cents also earned a 50% interest. That will be 25 cents. This 1.5 is the sum of our original dollar and the 50 cents we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, and we also have the 25 cents that these 50 cents made. A total of $2.25. This is better than doubling. If we want to understand this using a formula, it would be 1 plus 100% over 2, the whole squared. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year?
So this is basically the concept of M, right? Compounding period per year, right? Compounding frequency per year, right? So up to this point, nothing new, nothing difficult.
We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually very simple if you've understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4. We would approximately get $2.441 at the end of the first year. I suggest you pause the video and understand the quarterly growth diagram really well. The 100% is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n, the whole raised to n. Clearly, more the number of time periods, higher will be the returns. This will give us the dollar value at the end. I probably know what your greedy brain is thinking. Is it possible to get unlimited money? Let's make a table now. Number of time periods and the dollar value in the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year into 12 equal time periods, my return will be higher than this. If I divide it into 365 equal time periods, It will be even higher. This tells us that a dollar at the start of the year will become these many dollars at the end of 1 year if the number of time periods is 365. So if we increase this number significantly, that is if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the returns improve, yes, but they converge around a value which approximately equals 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding a 100% growth over one time period. Yes, that's E. Don't forget, we had assumed a 100% growth here. And that's what E is. It's the maximum we get after a 100% continuous compounding growth over one time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2. But after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means the digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely. There's no problem at all. In general, the growth after continuous compounding is given to us as e to the power r times t, where r is the rate and t is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as e to the power 2 times 5. We squared e to include 200% growth, and we raised it to 5 as there are 5 time periods. It'll give us e to the power 10. E is nothing but the maximum possible result after continuously compounding a 100% growth over one time period.
All right. So that's the basic, concept of Euler's number. It's pronounced Euler. Swiss German mathematician. So time is 7:20, 7:21. So I think it's well past the time to take a break. So let's take a 10-minute break and reconvene at about 7:31. Okay, All right, 10 minutes. 10 minutes. All right, we're back. We're back. So let's wrap up the rest of the video. I mean, this one we watched, right? But let me know. I'm wrapping up. I'm summing up a few things, summing off a few points from this
discrete time and continuous time, right? As you saw in the discrete time and important concepts are introduced. One is the discrete time and continuous time, right? As you saw in the example of the boy growing, in nature, nothing grows in discrete or in discontinuous fashion, right? The growth happens gradually and continuously. Everything grows that way, right? It doesn't grow at the growth doesn't happen just instantaneously at the end of the year or at a strike of a clock. Now, also, if you think about it, the time we understand the nature of time. We understand time as minutes, hours, seconds, days, weeks, months, years, and these are all discrete units, right? Discrete units. But think about it. Time never declared itself in a discrete unit. It's all a result of human intervention. Isn't it right? Time just flows quietly without saying anything, right? Time just flows smoothly and seamlessly and continuously, right? Without making any announcement like, it's 1 minute, it's just, 2 minutes, right? So time by itself is continuous. And then and since the growth is continuous, how do we capture that smooth continuity or the smooth fluidity of that growth over time? Well, think about it. The best thing we can do is by splitting time into smaller fragments, right? Just like this. At first, the 1 year was split into half years, right? And then in the next, the 1 year is split into 4 quarters. And as we continue to do this, let's say, 1 year is 365 days, right? And then 24 hours times 365 will express 1 year in hours. Times 60, that times 60 will express 1 year in minutes, and that times 60 will again express 1 year in seconds, right? And what is smaller segment? What is smaller unit than second? 1/10 of a second, 1/100th of a second. I mean, have you ever heard of nanosecond? What's a nanosecond? Nanosecond is a 1 over 1 billion. In other words, 1 billionth of a second, or it's called, also 1 to the negative 9. 1 to the negative 9 power, right? Negative, you remember x to the negative 1 means 1 over x. It means reciprocal, right? So x to the negative 2 is 1 over x squared. So nanosecond means, nano means 9th, right? Therefore, if you split time, I mean, how finely, how infinitely fine fragments can we break the time up? There's no limit, right? There can be even, 1 billionth of a 1 billionth of a second. But then, because there's no limit to that, it's a futile effort to try to break it up like that. So, let's continue with the video, and in the next segment, it will give you the example. All right, another thing, the n they use here is actually in our model n. Remember the compounding frequency per year, n, right? Now, so, and our n is the result of m times t, the number of years. I mean, they can use n as the number of compounding frequency or number of compounding per year because they have only 1 year timeline. If you have multiple year timeline, we need to distinguish between n and m, right? But anyway, if you understand, as long as you understand, this is the notation we have been using is m, then that's fine. So let's continue.
Okay, so this video is practically over. So let's go to the next one. So
time value of money, solving for n in single cash flow model. So let's pick up from where we left off. So in part 1, we ended the video with the discussion about the Euler's number, and you saw the video also, specific video that was embedded in this video, right? About what Euler's number is. So, and if I can sum it up, right? Let me just sum it up in a more compact way. So our question was, if we increase the number of time periods, in other words, we are trying to find what this would be when we increase this m, right? So in that small video, right, they increased m to 1 million, right? And by the way, you all understand what this APR over m is. That's the periodic rate, isn't it right? In other words, if annual interest rate is 6%, and if the compounding frequency m is 4, right, this would be the quarterly rate, 6% divided by 4. So that would give you 1.5%, right? That's also called the periodic rate, meaning, you know, the rate that applies each period. You know, each period the principal gets compounded, right? So in that video, we put 1 there instead of APR. That's fine, because 1 is 100% APR, and it can be 10%, 6%, whatever. But 1 is putting 1 there is a nice way of simplifying everything. So then our question is, what if this m goes to a very large number, not just 1 million, but what if it goes to the infinity? What if m goes to infinity? Think about it. When m is infinity, then APR over infinity will be what kind of number that will be. Now, let me rephrase it, or let me just put 1 there to make it simple, be easier to think this way. So that means, what if that m goes to infinity? And we can rewrite it as 1 plus 1 over infinity, and the whole thing raised to infinity. Now, since you already saw the video, you understand the meaning of 1 over infinity. That means, look, if we increase the compounding frequency, or the number of times we split 1 year, right? So in other words, so far, you know, 365 was the generally maximum segmentation of 1 year. But then in the small video that you saw in part 1, they raised that to 1 million. But it doesn't have to stop there. As I said, you know, it could be 1 billion, 1 trillion. But of course, you know, for all practicality, 1 trillion, 1 billion is not really necessary, right? But, you know, let's just call that infinity, right? I mean, infinity would be, you know, much greater than, you know, 1 trillion, you know. But anyway, what's the difference? I mean, a very, 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 very large number that we cannot even count, or that we don't even have names for, right? We'll just call it infinity, right? So think about it. What would this number be? 1 over infinity. Now, when I ask a question like this, very, you know, oftentimes I hear some students, you know, just blurt out, you know, without too much thinking. They just say, oh, 1 or infinity or 0. Now look, some people just you know, blurt out 1 or infinity are not thinking at all. I'm sorry to say this, but, you know, it's deplorable that that is the current landscape, or the current, you know, the reality of math education. Because in math classes, you're not trained to really think. But, you know, some people are really, you know, they learn to think. But some people just, you know, pick up something, you know, like when they say, oh, if the problem involves, you know, some complex variables, or complex, you know, concepts like infinity, usually the answer is either 0 or infinity or 1. Look, we can do a very simple thought experiment. I mean, it doesn't take that much, right? You should be people. You must be trained to do some thought experiment, because without thought experiment, people just end up, being incapable, completely incapable of any thinking. Now, what is the thought experiment here? Look, if you divide 1 by 10, that's going to be 0.1, right? And divided by 100 is going to be 0.01. If you divide 1 by 1,000, then 0.001. And then if you divide it by 1 million, it's going to be 0.501, right? So what does that mean? If you divide it by 1 billion, it's going to become 0.901. In other words, the greater the denominator, right? In other words, if the more you increase the m2, right, the smaller the number gets. And it doesn't take that very high intelligence. And someone with any average intelligence can easily arrive at that conclusion by doing a simple thought experiment, right? So then, what would be the result of dividing 1 by infinity, right? It cannot be infinity. It will be a very, 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 very small number. Isn't that right? Some people who would say 0, yeah, they are at least doing some thinking, right? But because it's going to be a very, very small number. But just because it is a very, very small number, it doesn't mean it is 0. It will be close to 0, but it will never be 0, right? And now there would be some other people who would say 1. Look, if that's also the evidence of lack of any thought experiment. How can it be 1? To make it 1, it would have to be either 1 over 1 or infinity over infinity, right? So people who just jot out or interject anything that comes to their mind are just simply exhibiting that they never did any deep thinking. And now the deep thinking doesn't have to be very complex one. It can be a simple logical thought experiment, right? That simple logical thought experiment is what makes the whole difference, right? What makes it completely different, right? The logical reasoning. This is what I call the logical reasoning and analytical thinking. And that's what you need to learn from this class, right? The math itself is not that advanced. It's not really like rocket science. The math itself can be all mastered if you can do just some logical thought experiment, right? Now, anyway, to continue with this discussion, let's get back to our question. My question was, what would this number be? And we understand, now we have the answer. This number, 1 over infinity, will be a very, very small number. Now, there is a name for that. There is an adjective for that. Infinitely small number, right? So it is called an infinitesimal number. Infinitesimal. That means infinitely small. So now, we have a problem here. Why? What is going to be this the result of the thing in the bracket raised to infinity? I mean, if the thing in the whole parenthesis, if 1 over infinity is, if this is 0, then the whole parenthesis is 1, and then it will be a very simple. The answer will be very simple. It will be your life will be very easy, because the whole thing in the parenthesis is 1. If you raise that thing to infinity, will still be just 1, because it's 1 raised to infinity. 1 times 1 times 1 times 1 times infinitely times 1, still 1, right? But the problem is, it's not 0. It's just slightly greater than 0, right? So this whole number, right, the whole parenthesis is just slightly greater than 1, slightly, just infinitesimally greater than 1. And if you raise that number to infinity, what's it going to be? That's what we found, right, in the video. That's the result will be an irrational number that approaches 2.718. And once again, we don't use the number. We call it E, or Euler's number, or exponential function E, right? Exponential E. Now, and this becomes the base of the natural law, right? Why? Because when we take log of a certain number, like any random number like x, you cannot take the common log of that, because once again, common log, you can easily take common log of numbers like 1,000, 1 million, 1 billion, which are basically powers of 10, and mentally you can easily, right? Because mentally you can easily calculate what is 10 to the 6th power, or 10 to the 9th power. But if it is number like 1.37, how do you know what would be the exponent of 10 that would arrive at 1.37, right? In other words, if that is not a neat power of 10, it's going to be very difficult to mentally process it. Of course, it doesn't mean it cannot be done. It can be done by a computer or by a calculator. But just with the human mind, it's not that easy to calculate it. So, but then we can take the log of any random number to base e. Why? Because of this property of e. E is based on the number that is slightly greater than 1. Now think about it. If 1 is used as the base of log, then it's totally useless. Why? Because raising 1 to any number cannot arrive at anything but just 1, right? So using 1 as the base, you cannot take the log of any number. But if it is slightly greater than 1, it will be a different story. So now you see why we need to use natural log to take log of any random number. And natural log of x can be written this way, or also written this way. ln of x. Of course, ln stands for natural log. Okay, so now, if you're okay with this, I'm going to erase this and then get back to our. So then think about it. Our problem was we wanted to use z equals x times y structure, right? Because when it is in multiplicative structure, then you can solve for x or you can solve for y, right? But we had z equals x raised to y structure, right? So we had to take the log to linearize it, right? So you had to then take the log of x, the left-hand side, and then you take the log of the right-hand side, and then it becomes this property of log, right? You can bring the exponent down just like a multiplicative structure, right? Multiplicative function, right? So y times log of x, right? If you have forgotten, right? Go back to video 1 and review this part. But our question was, what is going to be the base of the law, right? I mean, because x and y are all random numbers, we cannot use 10 as the base, right? So that's why we needed to. That's where this natural log comes in. So now we have natural log. If we take the natural log, because you can take any log of any number, any random number, if you use natural log, then it becomes natural log of x raised to y, which is again then y times natural log of x. Okay, now I know it's it doesn't look very nice because it's very hard to write on the whiteboard using the mouse, but now you get the idea. We have fv over p in the left-hand side, and then we have 1 plus r on the raised to n on the right-hand side. And to solve for n, we log linearize, or we take log and natural log on both sides. Okay, so we come to fv over p, natural log of fv over p, and then n times natural log of 1 plus r. Okay, and solving for n, if you want to solve for n, what do you need to do? If you solve for n, then you divide natural log of fv over p by you divide that by natural log of 1 plus r, right? Okay, hence we arrived at formula. And you might say, some people might ask me a question. They might say or complain, Professor, I barely understand the concept of natural law logarithm, and then how do I calculate natural law? Look, that's totally unnecessary to worry about that, because you don't have to calculate the natural law. You only provide this logic to Excel, and Excel will execute it, right? You don't have to bother with the calculation. That's why we use Excel. So I'm going to switch to from the whiteboard to Excel. So let me okay. Alrighty, so the time value file, and you downloaded it, and in the last class, and I've been telling you to save this work every time we work on this file, right? After we work on this file, you must save the work because it's your work. You have to save it, and since we are going to, since we will continue to use this file, the work needs to be updated every time you work on it. So now I want you to go down to row 13, and from row 13, I want you to delete all the highlighted cells, okay? All the highlighted cells, okay? And what I want you to go to row 20, and row 20 is actually a recap of what we did in the last class. In the last class, we solved the future value equation for R, the rate, right? In this example, the scenario is quite obvious. There's P, principal. If you have this principal, you put this principal in the bank, and your timeline is 5 years. In 5 years, you want to grow it into this future value, and the compounding is fully. So what does that mean? N would be 20 because there are 4 compoundings per year. So for 5 years, there's going to be 4 times 5, 20 compoundings, right? So our next question is then, what's going to be the rate? And this rate means periodic rate. It's quarterly rate in this case, right? Because when compounding is quarterly, right, the relevant rate is quarterly rate, not the APR, not the annual rate, right? Now, so, but remember, all rates, all returns, all interest rates are expressed in annual basis, right, on annual basis. So we will eventually, once we find the quarterly rate, we will eventually convert it into APR, which is not a difficult thing. Now, once again, that's why the highlight is yellow here and APR is olive green. Why? I told you, I've been telling you, there's a meaning to the color of highlights. It's not just randomly picked. It's not arbitrary. The consensus, the convention is yellow highlight for the primary solution cell. That's the solution cell. Now the lighter, light green or olive green, this is the reserved for secondary solution or intermediate calculation, right? So we will first, because this is our primary solution, so we need to know what the quarterly rate is. And you see, I don't need to show this to you again. So we'll put that formula there, right? We'll put, we are solving for rate. So this is the rate where, this is the formula we're going to put in there. So it's going to be FE P raised to 1 over N is in F20, and you cannot click it in because the formula is covering that cell. Then in that case, what do? Well, you'll have to manually type it in, F20, right? What I'm saying is manually typing in the cell number, not the value of N. Why? Because that's called the soft coding. Whereas entering the actual numerical value is called hard coding. But you should never hard code. Why? Because once you do that, the formula gets fixed for that problem only. It cannot be reused or recycled for other problems, right? But if you soft code, this formula can be copied over and replicated in different problems of the same pattern, right? So that's the benefit of using Excel. If you have to enter the data every time you do that, then what's the point? You have to build a formula into it all over again, right? But that's the downside of the hard coding. But if you soft code it, it can be copied and pasted into new problems, right? It raises efficiency, right? It makes your life a lot easier. So now the formula is then -1, and this is once again called geometric average, right? And hit enter. We get this, and then what is the annual rate then? Since this is the quarterly rate, the annual rate is simply that times 4. Here you go. We got that. As soon as these numbers are filled in, these cells are also filled in as well because I entered already in the cell that this cell is equal to this cell. So once I get that, this is automatically populated. And this one is also automatically populated because I already had put in there. Okay. Now our next question. So row 21. And the row 21 is the paired problem. It's paired with number 20, so we already know the answer. N will be 20, T will be 5. But then we want to confirm that, right? So how do we confirm that? Well, using the formula for n, and then, so what is it? Natural log of FV over PV, and once again, FV, we cannot click it in, so then I'll type in G21, and then over P, right, or natural log of 1 plus R. Okay. If I hit enter, it's going to give me 20. And if it's 20, then our formula checks out. Okay. So hit 20. Yeah, I got 20 there. And then converting that into years. 20 quarters are 5 years because, 4 quarters per year, right? So we simply need to divide that by 4. Hit enter. It's 5, right? So the formula checks out. Now, we also want to verify this by making this equal to, making our example equal to row 6, right? Because in row 6, if I change present value to principal to 10,000, future value to 13,000 for something, right? The same number as that, then we should exactly get for this, we should get 6%, 1.5 year, and we should get the same result as that, right? So let me quickly simply change this to make that equal to that one, right? And make this also equal to that, right? Okay, so I got 1.5 for quarterly rate, 6% APR, 20 quarters, 5 years. Of course, that was also, see, our formula really checks out. Now, let's go to row 13. And what is row 13 through 16 about? Now, let's think about it. It's also 5 and n. But in this example, what's the difference? The difference is this example, this model is slightly more detailed. In other words, R and N are outside the formula. These variables are adjusted outside the formula, right? Quarterly rate and total number of compounding are outside the formula, right? So the formula can be simple. But here, that adjustment is not made outside the formula, so we'll have to make that adjustment inside the formula. And that will make a formula more complicated. Okay, so here, basically, we'll have to do FU PV, right? FU over P, and then raised to 1 over n. And our n is, in this case, it's going to be 20 because 5 years and quarterly compounding, right? So 2, it's not just 5 because there's quarterly compounding. So we'll have to make that adjustment here. So we'll have to type in C13 times B13, okay? Oh, okay, here's something. C13 times B13, close the parenthesis, right? And then close the parenthesis again. So only for the denominator, right? And you understand if I didn't put the parenthesis here, without the parenthesis, what's gonna happen is this is gonna happen first, and then this will happen later. So we don't want that. I mean, it has to be, the denominator is a whole chunk. So that's why you put the parenthesis. It's always in a PEMDAS, right? Now, then -1. So what do you expect? You will get, is that APR? No, actually what we got there was not APR, it is the quarterly rate, the periodic rate. So how do we convert it into APR? So then we will have to multiply the whole thing because that will give you the quarterly result, and we must multiply by 4. But once again, do not manually type in 4, right? Because that will be hard coding. If it is hard coded, you cannot use it in other situations. Now 4 is in D13, so you simply divide multiply by 4, that D13, and then you get this annual rate. Okay. Now n, so we know already it's going to be 5, but let's see if it checks out. So take the natural log of future over present divided by natural log of n plus not APR. First of all, you will understand the relevant rate is quarterly rate because we are dealing with quarterly compounding. So what do? You'll have to adjust it or divide by adjusted by 14. Okay. Hit enter, and what do you think you will get there? You're not going to get 5 there. You're going to get 20 because we are dealing with quarterly compounding. So that's 20. That means 20 quarters. But you have to answer in years because we are dealing with year, right? The label says you have you have to answer in years. So what do? you to convert quarters into years, you'll need to divide it by 4, and 4 is there in D14, so you enter D14, enter, there you go, gives you 5 years, right? Now, in row 15 and row 16, compounding frequency is 1, so it's annual compounding, so you don't have to bother with making adjustment. But again, it doesn't hurt. I'm going to copy that and paste it here. Oh, look, if it is 10,000, 10,000, this is not going to work. So I'll have to make it equal to that, and also make it equal to that. Okay. Now it's going to be annual 24.57%, right? You notice that, oh, that's greater than this one. Of course, we are doing annual compounding here, not quarterly, right? If you're doing quarterly compounding, that means with the smaller interest rate, you can get to the same future value, right? It takes less interest rate to get to the same future value. But if it is annual compounding, of course, the rate has to be greater to take this 10,000 to 30,000. Make sense? Now, this should be pointing to, for this example, it should be pointing to that. Now, again, I'll just copy this and paste it there. Okay. So we got 5, not because the number is copied, but because the formula is copied. But look, because the adjustment is made, D16 is, right, the compounding frequency, and in this case it's 1. Look, your 1 is not doing anything, right? It's completely innocuous, right? So in other words, although in annual compounding it is not necessary to use this, right? But the benefit of, I mean, even without D16, that adjustment, you still get the same answer. But what is the benefit of, this is more complicated, but what's the benefit of using that? I mean, well, it's because of the uniformity and consistency of the formula structure. Because if you don't, if that structure is universal, because under any n, right, under any compounding frequency, it can be used. But if you don't use this, if you don't make this adjustment in the formula, right, then it can only be used for the case where m is 1, right? So that is less productive or less efficient, right? If the formula can be used for only a specific occasion, then that is totally useless, right? When the reason we are using a computer model is because it can be universal, it can be replicated, right? So whatever is taking away that benefit of universal applicability is not something we want to do, right? Okay, the same thing goes for this. I mean, this adjustment was not necessary for annual because it's 1, and 1 is innocuous, right? It doesn't do anything, it's harmless. But for the benefit of consistency and uniformity of the structure, right? Once you build the model, you have to always have the universal applicability in mind. Okay, alrighty. So that wraps up everything about today's lecture. Which is about how to solve for n in a time value of money single cash flow model. Okay, so this concludes part 2 of the video of this lecture.
All right, so that wraps up everything about the single cash flow model. And of course, I would like to ask if you have any questions, and I don't think any of you would have any questions at this point. You are probably even busy digesting what's been presented. Obviously, it takes time. It takes time. You have to work on it. And you have to digest it and regurgitate on it, and really, to make it part of you. It takes time. So at this point, I don't think any question comes to your mind. But if you do, please, feel free to ask. Don't hesitate. Feel free to ask. Okay. So I mean, questions like, why is it single cash flow? Or what is can you explain Euler's number again? Of course, some questions I cannot answer within the next 10 minutes. We have only like, but any question, I mean, if I can, if we don't have enough time, then I will answer it tomorrow. But at least let me hear. And obviously, everything is still very cloudy in your mind. It must be still very cloudy in your mind. But feel free to ask. Okay. Any questions? So since you're not asking any questions, let me just also take you to the announcements. And you guys must have received email already. Quiz one instruction, right?
Yeah.
Yeah, this was sent out. So it's gonna start this Friday. And quiz one is so basically, topic one and topic two, right? Topic one and topic two. So please, study, go over the lecture videos in topic one and topic two, right? And what else? So there are like, I don't know if I remember correctly, but it's mostly this is multiple choice questions, multiple choice. I think there are like 25 to 33. I don't know exactly, but 25, either 25 or 33 questions, multiple choices. Maybe some could be short math, short answer, mathematical questions. So yeah, that's it. And any other questions? Any other? So depending on, let me just, yeah, somebody was trying to say something.
No, I said no question.
Okay, good. So let me just quickly check what is going to be tomorrow. Right. Tomorrow, oh, we already sort of a little ahead, one day ahead, kind of one day. So tomorrow maybe we can do actual Excel exercise of the time value of money examples. Okay. All righty. So
thank you. Appreciate it.
All right. You're welcome.
Thank you.
So if there are no more questions, then class is dismissed.
Have a good night.
You have a good night. See you tomorrow.
All right. See, somebody was asking question, or I thought you were just saying greetings. All right. Take care, everyone, and I will see you guys all tomorrow. Okay. All right. All right. You're welcome, Zaniev. All righty. Take care. All right. So I'll stop recording.